Bismillahirrahmanirrahim. Relation between exact differential and conservative field. So in this video we are going to connect these two concepts, conservative field with the exact differential. So the differential f dr is exact if and only if if and only if f is conservative. So this differential be exact if the field is conservative. We have to prove if and only if the field is conservative. We have to prove this argument. So let f dot dr is exact. Then we can put it as exact differential. Exact differential. Okay. Then we can put it at exact differential of scalar function phi. This implies f1 dx, this is 1, f1 dx plus f2 dy plus f3 dx, this is from the left side, this is equal to partial phi partial x dx, partial phi partial y dy, and partial phi partial z dz. On comparison we have f1 is equal to partial phi partial x, f2 is equal to partial phi partial y, and f3 is equal to partial phi partial z. This implies that the field f1i, f2j, f3k is equal to partial phi partial xi, partial phi partial z yj partial phi partial zk. Following these three equations, the field is this. So that implies the vector field is equal to gradient of phi. This implies the curl of f is equal to the curl of grade of phi. This is 0. So the curl of f is 0 mean this means that f is conservative. So if f dot dr is exact differential, then the field is conservative. Now let's prove the converse. If the field is conservative, then if the field is conservative, if the field f is conservative, then okay, then we have f should be equal to grade of phi. Conservative field satisfy this equation. This should be grade of phi. This implies f dot dr grade phi dot dr. So f dot dr is equal to d phi. We know that grade of phi dot dr is d phi. This is very simple. Grade of phi mean partial phi partial x I, partial phi partial yj, and partial phi partial zk dot with dr. Dr mean dxi, dyj, and dzk. Taking the dot product on both sides, this is partial phi partial x dx, partial phi partial y dy, and partial phi partial z dz, which is exactly d phi. So these two vector, the dot product of these two vector is d phi, but d phi is exact differential. But d phi is exact differential. This implies f dot dr is exact differential. So if if the field is conservative, then f dot dr is exact differential. And why we need it, why it is important, because when we find the work done in a field, and if it is conservative, then it is easy to find the work done. We know that the work done is equal to, from some point 1 to 2, f dot dr. This is the work done. If this is exact differential, mean if the field is conservative, then we can put f as grade of phi dr, and that is equal to d phi. So phi from P1 to P2, that means phi at P2 minus phi at P1. This is the work done by the field. So the work done become independent of the path. We need only the final and initial position. If this is our case, when this f dot dr is exact differential, then the work done become independent of the path. Only we need the initial and final points. Okay, let it be conservative field such that f is minus grade phi. So if it is conservative, it will be either minus grade phi or grade phi. Suppose a particle of constant mass m to move in this field. If a, b are any two arbitrary point in this field, prove that. So we have to prove this equation. Now we know that f is equal to ma, and a is d square r dt square. It's the second derivative of the position vector. Then we can put this in this way by 2 okay, let me take the dot product of this equation with dr dt on both sides. So this is m dr dt dot d square r dt square. So we can put it m by 2 d by dt of dr dt square. This is in fact length square, velocity square. So you can see that if I differentiate this, the 2 will be reduced, the power reduction. So this 2 will cancel, we will get m, and this inner function, that is this one, and the second derivative of the inner function. So that is okay. Now integrate this equation with respect to t from point A to B. Integrate from A to B on both sides. F dr dt and dt is equal to m by 2 is constant, so integrate from A to B. D by dt of dr, so let me put it velocity square. This is velocity square, and dt cancel, this dt cancel. What we get a integral from A to B f dot dr and so this is in fact the work done from A to B by the field. And here we have m over 2, and the differential and integral cancel, v square from A to B. So this is equal to m by 2 v at B square minus m by 2 v at A square. So this is equation number 1. This is work done by the field force F moving the body from A to B. Okay, now the potential will do this work. So the force field is conservative, and this is equal to minus grade of phi. Take the dot product on both sides with dr. So, and then take the integral from A to B on both sides. So this is the work done. This is the same work done. And here we have the exact differential. This is d phi. So that means minus phi from A to B. So putting the value minus phi at B minus phi at A. So this work is equal to phi at A positive minus phi at B. This is equation number 2. Equating 1 and 2. Equating, so 1 is equal to 2 implies because both equal to work, so m by 2 vb square minus m by 2 va square is equal to phi at A minus phi at B. Rearranging, we have m by 2 vb square plus phi at b is equal to m by 2 va square plus phi 8a. So what is this? This is the kinetic energy of the particle at position B, potential energy of the particle at position B, kinetic energy of the particle at position A, potential energy of the particle at position B. So this is the total energy at position B, and the right side is the total energy at position A. So this is conservation of energy. So as we are in the conservative field, so the energy will conserve, and that is the proof of the conservation of energy. So in conservative field, the energy of the particle conserve, it remain the same. So we prove this assertion. If we have a conservative field, we have this equation that energy at position A should be equal to energy at position B. It will not the total energy will not change. Okay, if this is helpful, this video is helpful, then like, comments, light in comments for improvement. And subscribe for help. Thank you.